This is section 2.7, inverse functions. This front slide right here gives us some nice pictures of graphs with functions and their inverse, but we're going to talk about one-to-one functions first, and then we'll get a little bit more into that. So speaking about one-to-one functions, so let's think back to when we checked to see if a graph was even a function or not, right? And so if we did a vertical line test, we would be able to determine whether it was a function or not. So if I was to take a vertical line and scan my graph from left to right, if at any time on that graph my vertical line was touching more than one point on the graph, then it would not be a function. But if I took that vertical line and swept it across and it never touched more than one point at a time, then we would say, okay, yes, it is a function. Well, now the way that we check to see if a graph is a one-to-one is by doing the horizontal line test. So it's like, okay, once we see that it's a function, then we check, well, is it a one-to-one function? And it's almost checking for the opposite. Essentially, you are, because when we're doing the vertical line test, we're trying to see, okay, is every single x only paired up with one y, right? If we had more than one y for an individual x, well, then we would have 2 points touching that vertical line, right? Well, now for the one-to-one, it's the flip. So it makes a little more sense, I think, once we see it. Okay, so this first one, if I was to take a vertical line across from left to right, it would pass the vertical line test. It would be a function. And then if I took a horizontal line, I could swipe it downward on the graph or upward. And at no point would I be touching more than 1 point on the graph, right? So it would also be one-to-one. So that one would be a one-to-one function. Then looking at the second one, okay, if I took a vertical line across it, it would pass the vertical line test, right? So it is a function. But if I did the horizontal line test, it would not pass that test because look, it touches 2 points at one time on that horizontal line. So it is a function, but it's not a one-to-one function. Okay, and then on this third one over here, if we did the vertical line test and took a vertical line and just swept it across from left to right, it would be a function. And then if we did the horizontal line test and I just swept a horizontal line down, it would also pass that test. So it would be a one-to-one function. Okay, let's look at this one down here. If I swept a vertical line across that graph, it would not be a function because it's touching 2 points, meaning that at that x, there are 2 outputs. There's 2 y's, right? And we see that that would happen at multiple spots on that graph. So that one's not even a function. And then looking at this one right here, we see going from left to right, if I took a vertical line across, it would check out as a function. And then if I did a horizontal line and swept it downward, it would pass that horizontal line test as well. So this one would be a one-to-one function as well. So vertical line test is truly what the name says, right? You just sweep a vertical line across and that tells us whether it's a function or not, if that graph is a function or not. And then horizontal line test, true to its name, you just sweep a horizontal line over the graph. And that tells us whether it's a one-to-one. Okay, so if it passed both those tests, then we're like, okay, that means that this graph has an inverse. So when we go to graph the inverse of a function, we literally are just switching the x and the y. So notice that the original function f of x has the 2 ordered pairs -3, 0, and also 0, 2. So for the inverse, which let's talk about that notation a little bit, this looks like you would say f up to the -1st power, right, of x. And really that notation is communicating that that is the inverse of the function of f of x. So when we see that notation, we're like, okay, the inverse, the x's and y's will switch. So notice that the ordered pair over here was -3, 0. Over here it's 0, -3. And then this ordered pair is 0, 2, and the inverse is 2, 0. So that is the only change. And understanding that change will really help you later on when you're rewriting the actual function to write the, well, I say rewriting the actual function, but writing the inverse essentially. So keep that in mind that when we're talking about the inverse function, the x's and the y's just get flipped. That's the only thing that happens. So to graph it is pretty easy because if I see those ordered pairs, I could say, oh, I can just take those ordered pairs and flip the x and the y. So they want us to graph the inverse. So we have 0, 2 and -3, 0. Okay, so inverse function, I'm just going to flip these around, 2, 0 and 0, -3. 2, 0 and 0, -3. Oops. Went off-roading a little bit, drawing my line. Okay, so notice where there's a reflection. If I was to draw a dotted line, this diagonal dotted line through the origin, I could fold it right there and it would be an exact reflection. Notice that's the same case up here. And then if we're to go back to our first slide, we see that as well. So that is where the reflection occurs. Oops, went too far. So all we do to graph the inverse of a function is take the ordered pairs that are given or ones that you can easily see on there and flip the x and the y. Okay, so they say the graph of a function f is shown. Use this graph to draw the graph of its inverse function. Notice that they showed us a picture, but in the original question, they didn't give us the ordered pairs, right? But they're very easily located. So it's -4, -4. That's this one right here. -3, 0, and 2, 4. Okay, so to graph this, just going to flip those around. -4, -4, 0, -3, and 4, 2. So -4, -4, 0, -3, and 4, 2. Connect the dots, and voila, that's what we're looking for. Okay, so when I go down to my answer choices, be careful because notice that a lot of them look similar, right? And it can be a little bit tricky. So I would actually look for those ordered pairs. I wouldn't just try to match up the picture. I would actually locate those ordered pairs. And we can't do it on this slide, but when you're actually in My Math Lab, you're able to press the magnifying glass and make that graph larger. So that's what I would actually do. Okay, so we look for -4, -4. This one doesn't have it. This one does have it. That one has it. This one has it. This one doesn't even have it. Okay, we're looking for 0, -3. Nope, this one doesn't have it, but this one does. And then I still would check my last point, 4, 2. So my answer will be C. And all we did was take those ordered pairs and then flip the x and y. Okay, so that's when they actually give you the graph, right? And we have ordered pairs. But now when we actually have the function written out as an equation, we can also write the inverse function as an equation out too. So notice that the very first thing you'll do is replace f of x with a y. Then you'll switch the x and y, which I think that's sort of your reminder of what you're doing. So let's say you see it and you're like, man, I don't even know where to start. Well, hopefully when you think of inverse functions, you think, oh yeah, x and y's are switched. So that will hopefully signal you to say, oh, I need to change that f of x to y because I need to be able to switch my x and my y. So switch your x and y, then you'll solve for y, and then you'll replace the y with the inverse of x. So we know that, okay, this is the function for the inverse of x. So let's go ahead and try that. Okay, so step 1, we're going to replace f of x with y. Okay, so now I have y equals 3x minus 4. Then I'm going to switch my x and my y. So I have x equals 3y minus 4. And then I'm going to solve for y. So isolate it, get it by itself. Divide both sides by 3. I get x plus 4 over 3 equals y. I'm actually going to flip that so that I have the y on the left side. Since I flipped everything, nothing changes, right? And now my last step, step 4, is to replace y with inverse of f of x. And this is my inverse function. Okay, and we can graph these. So if I was to graph 3x minus 4, and then in the second slot put x plus 4 over 3, you would see that graph that shows that nice reflection over that diagonal line. Okay, so this one's telling us to find f of g of x and g of f of x and determine whether the pair of functions of f and g are inverses of each other. So the f of g of x and the g of f of x, if you're like, what are you talking about? I would highly recommend to go back to video 2.6 where we talked about composite functions and plugging functions into each other. And so that might help a little bit. But basically we're plugging one function into the other. So this is a way for us to see if f and g are inverses of each other, because if I plug one into the other and then I do the, opposite, plug the other one into the one that I didn't plug it into the first time. So f of g of x, and then plug f of x into g. So find g of f of x, and they both equal x, then those are inverses. I can show you better than I could probably tell you because that just sounds like a lot of mess right there. So plugging g of x into f of x, I get 5 times something minus 6. I'm going to plug. So notice that this is what I just wrote out, right? But I left x blank, and this is what I'm plugging into there. And I'm doing that because they told me to plug g of x into f, okay? Five times x plus 6 over 5, this will cancel out because I'm dividing by 5 and then I'm turning around and multiplying by 5. So I'm back to where I started. So I just get left with x plus 6. and then minus 6 from the outside of the parentheses, which just equals x. Okay, so let's say that I did not get x right there. I could stop. I would check my math to make sure that yes, that the answer I got truly was the correct answer. But if I don't get x there, then it doesn't matter if I get x for the second one. They cannot be inverse functions if I do not get both equal to x when I find f of g of x and g of f of x. Okay, so now I'm going to write g. So x plus 6 over 5. Go back and plug in f of x, 5x minus 6. Simplify, 5x minus 6 plus 6 would just be 5x over 5, which would simplify to just x. Because when I plugged in each function into the other function, it ended up simplifying down and equaling x. It happened in both of them, then these are inverse functions. It has to be for both though. Again, if plugging one function to the other one throws you for a loop, definitely hit up video 2.6. Okay, same thing. They say find f of g of x and g of f of x and determine whether the pair of functions f and g are inverses of each other. All right. Now, be careful because sometimes students say, oh, I see the pattern. If you have multiplication with one number and then, subtraction with this other one, well, on here we had division, so the opposite operation with that same number, and then the opposite operation with that same other number. Then they just start trying to look for the patterns and not do the work. And be careful because sometimes that is not the case, because look, I have a 7 and an 8 involved, right? So I see a 7 and an 8, I see multiplication and subtraction, I see a 7 and an 8 over here, and I see the opposite operations, addition and division. And so a student can be misled and say, yep, those are inverse functions automatically. So let's actually do the work and see. All right, so 7 times x minus 8. My x in this case will be my g of x, which is x plus 7 times 8. So this would distribute out. I would have 7x plus 49 over 8 minus 8. I'm going to rewrite that 8 with a denominator of 8, so I can actually do the math between the fraction and the 8, the minus 8. So 8 over 1, if I want to rewrite that, I'd say, okay, I'm going to multiply by 8. So my denominator is 8, but I got to do the same thing up top. Okay, so now it's, oh, let me undo that. Okay, so now it's minus 64 over 8. So I can actually do the math. So it comes out to 7x minus 15 over 8. So that right there tells me, okay, did not come out equal to x, so it's not looking like it's the inverse. I'm still going to do the other one because on my math lab, it'll have you do each of them and then determine, say, okay, are they inverses? But we already know right now, because it did not equal x, that it doesn't matter what the other one equals. Okay, so I'm going to write g x plus 7 over 8. My x in this case is the 7x minus 8. 7x minus 8 plus 7 is 7x minus 1 over 8. And I cannot simplify any further. So I'm done. Okay, so these are not inverse functions because when I found f of g and g of f, it did not come out equal to just plain old x.